survived the storm. This morning's first talk of the Oscar. Quantized spaces of high-dimensional manifolds and applications of positive senior curvature metrics.
Thank you very much for the fantastic introduction and opportunity to speak here. So I want to explain sort of two things in this course of lectures. So the first two are about what I call moduli space of manifolds. It just basically means classifying spaces of diffeomorphism groups. But there's a particular model I want to talk about that it's sometimes to think of it as a moduli space as opposed to a classifying space. And then I want to explain some recent work of mine with Solomon about these spaces, and then I want to explain an application of this to something that sounds completely different, which is spaces of positive scalar covariance metrics. To begin with, even if we're only interested in naked manifolds, or manifolds with no additional structure on them, it's very important in this story to consider manifolds with structure on their tangent bundle, like orientations or spin structures or ... And I want to spend some time being a bit careful about that. So the way I want to set that up is as follows. So let theta be a map from some space to BOD, i.e. I have a space E and I have a d-dimensional vector. Okay? I'll call this a tangential structure. And the examples are all the things that you're used to. We can take BSOD over OD. If we want to do orientations, we can take B spin D over BOD and things of that flavour.
Don't you want it to be a vibration, or do you just want an arbitrary map?
For now, it's just a map. It can be a vibration later. And if W is a smooth, let's say closed for now, but I will relax this in a second, d-dimensional manifold, then I want to talk about the space of theta structures on W. And you may very well expect me to say something like, I've got B over BOD, and I've got W, it has a tangent bundle which is classified by some map, and talk about lifts or something like that. So that turns out not to be an excellent definition, because you have to choose this map. And whereas the manifold has a canonical tangent bundle, it does not have a canonical Gauss map classified as tangent bundle. So it's better to do something a bit more canonical. And the following works. You want to bund TW to the vector bundle that this map classifies. So this is the space of bundle maps. Okay? So it's just continuous maps from the total space of this bundle to the total space of that bundle, which are linear isomorphisms on every 5. So this is let this symbol be the space bundle maps TW to the bundle classified by theta, i.e. continuous maps which are linear isomorphisms. And you can topologize that just with a compact open topology. So you just think of them as continuous maps that happen to have a property of being otherwise linear. Okay, so now a theta manifold is a pair of a manifold and a theta structural manifold, which I'll usually use L for no especially good reason, except that when I used to do things that way, that was a lift, and so it was called L. Now it's not a lift, I still call it L. So it's a manifold and a theta structure on its tangent bundle in set 37.
If one composes with the map down to the bundle gamma D, wouldn't that give you the map from your L?
A map T.
A, right. So it's somehow in your L to choose the...
Right, so implicit in all this, the reason this works is because for any bundle of dimension D, space of bundle maps from V to the universal bundle is contractible. This is something that you know, right? And so really I'm picking the points in this space implicitly, but it's nice to build it in this way. So that's what a theta manifold is. It's a manifold with a theta structure. M, say, is a D minus 1 manifold. Then a theta structure on that is a theta structure on its one stabilized end. So the theta structure is bundle map on its one stabilized end. That'd be my guess. And now, if W is theta manifold, if WL is a theta manifold with boundary, and the boundary has a collar. So and we have a given collar. What am I calling it? W. Okay? Then we can differentiate that collar in this direction. So that we get an isomorphism in a canonical way by differentiating that collar. And so any theta structure on W induces one to that, just by precomposition with that map. So L on W induces L to the boundary. And now what I might want to do is fix a boundary condition and only look at bundle maps that satisfy a boundary condition. Fixing L naught then I just let bundle maps with a boundary condition on TW to here, satisfying the boundary condition L naught to be the obvious subspace. It's just the subspace of those bundle maps that when you restrict them to the boundary in this way, it's actually equal to the bundle map L0. So with respect to L0. Okay. So this is some yoga of theta structures on manifolds, and now I want to use this to make what I want to call a moduli space of manifolds with theta structure.
Can I ask you a question?
Yeah.
So there is, for example, if we take B spin B, and then there's this notion of equivalence of spin structures, and then usually one tries to argue that there is an obstruction of finding a spin structure, and different equivalence classes correspond to the homotopy fiber.
Right.
So how does this translate precisely?
How it translates it, so in this setting, firstly, so let's take this example, the spin example, then this space is going to not be empty. That's the obstruction to existence. And if it's not empty, then it will have various path components. Those will be principal space for the first mod 2 co-moduli of the manifold. It's a torso, right, for first mod 2 co-moduli.
So what's the equivalence relation kind of on?
Well, so the point now is a space. The equivalence relation is that now you can have a path between two maps in here. And if there's a path between them, you say they're equivalent. And if there's not, you say they're not. But it's even better than that, because the components of this space in that case are copies of RP infinity. And that's reflecting the fact that a spin structure has automorphisms. There's a non-trivial path from a spin structure to itself given by the spin flip. So this has, so if you just take pi 0, you get something that you might call the ordinary classification of spin structures, but you should remember the whole homotopy type. And that's important for what I'm going to do here.
But if
So-
you start with BSO, like you have two steps in some sense.
Yes.
Right. If you do BSO, then it's either empty, if it's non-orientable, or it has two contractible path components. Right. So now if so if W is the manifold and LW is the boundary condition. So this is not continuing further. And I want to fix one more piece of data, which is a contractible choice. It doesn't really matter, but I want to fix it anyway. I want to fix an embedding of the boundary of the manifold into infinite dimensional Euclidean space. And maybe I convenience later, I write 0 across infinite dimensional Euclidean space. Okay, now just pick one. That's a contractible space of course. Then I'm going to define a modular, so the way I want to read this sequence of symbols is the moduli space of theta manifolds of topological type W with boundary condition L naught. And it's just defined to be the following thing. And get the space of embeddings of W into the infinite dimensional half space. And they should be embeddings satisfying a boundary condition, and you can guess what the boundary condition is, because on the boundary of W in order to agree with my given embedding.
Including the color which you fixed, it should.
We're coming to that, yes. I'm going to say exactly what I mean by embeddings in a second. Then I want to cross that with the space of theta structures. Satisfying this boundary condition. And then the diffeomorphism group of W acts on both things. It acts on embeddings by precomposition with a diffeomorphism, and it acts on the bundle maps by precomposition with the differential of the diffeomorphism. Okay? That's the real reason why I wanted this model for theta structures, because it actually has a precise action of the diffeomorphism group. And then I wanted to take the quotient of this by the diffeomorphism group of W. And now I'd like to spend a second making precise what all these things are, involving things like collars and so on.
So, what diffeomorphisms which are the identity on?
I'm just going to write that now. So here, it's embedding space. So let me, for the next couple of boards, let me just shorten this to E, and shorten this to 1. Okay, so I'm sort of writing that all over the time. So E is the space of embeddings E, such that if I do the embedding on this column, that everything inside has a column which I wrote somewhere. I've chosen a column of W. So that's a map from -1, 0, plus boundary W, to minus infinity, 0 plus infinity. And it should be of the following form: Tx goes to T E naught X, at least for small enough t. Okay? And the epsilon is not part of the data, it's just the existence of an epsilon. Okay? So they're just things that are collared, not on the whole column necessarily, but they have a product structure at least on some small part of the column. Now, if you're going to take that as your definition for E, then you have to do a similar thing to your definition for diff, otherwise diff won't act on that. So when I write diff boundary, it's a bit more than just preserving the boundary, it's preserving a little column. So diff equals phi, such that C composed phi equals identity near the boundary done. Where near is an open neighbourhood, and in particular an open little column neighbourhood.
Confused about your range on T, the absolute value of T should be less than epsilon?
Yeah, okay. I changed my notes. My colours used to go the other way. Right, so this is what I mean by the moduli space. And now, why is this a good name? Well, this space E is contractible. It is embeddings into infinite dimensional Euclidean space. Okay? And you probably know an argument for why that is path connected. You make your embeddings use different collections of coordinates, and then you just use a derivative relation. If you think about that argument, that proves that it's k connected with k. Okay, so this is contractible, and moreover, a group of diffeomorphisms actually freely on the embeddings. Right? If I have an embedding and I have a diffeomorphism that fixes it, then it has to fix in particular every point, because an embedding is an injective map, and hence it has to be identity. Okay? Using, admittedly a bit more than that, you can show that the action is actually the best possible thing, so it has slices. So the quotient of E by diff is a principal diff bundle. I don't want to go into that, but if you've got a group acting freely on a space, and it's reasonable, then it's going to be a principal space. So this is nothing but a very particular model of the Borel construction of the group of diffeomorphisms acting on the space of fluid structures. That's what it is. I was just calling that bond for now. It's the homology quotient or the Borel construction or whatever you like of diffeomorphisms acting on fluid structures. Okay. Right. So this is supposed to be some moduli space of manifolds of type W, and if that's going to be the case, then it ought to have a universal family of manifolds of type W over it. And it does, a similar thing, E theta W, LW, L0, sorry, to be W cross embeddings cross theta structures. And then I divide out by the diffeomorphism group of W, where it acts diagonally on all three factors. Okay? This has a map to that by forgetting this factor, and the fibers are copies of W, because that's exactly what you've forgotten. So we get projection map, E theta W L naught, and theta W L naught, and this is a smooth fiber bundle with fiber W, and with one more property, which is that because these diffeomorphisms all fix the boundary pointwise, this is a bundle of manifolds with boundary, and it has a sub-bundle of boundaries, but that's trivial in a given way. Okay? So it's a smooth fiber bundle with fiber W trivialized along the boundary. Okay? And it has one bit of extra structure, which is that it has a relative tangent bundle. Right? All the fibers are manifolds, so you can glue together all the tangent spaces of all those manifolds, and you get a vector bundle over the total space. If you want to construct that carefully, you can just do exactly, so I'm writing T pi, so the relative tangent bundle of this space. Just do exactly the same thing, but you've got place W by its tangent bundle. And And this now, the tangent model of W to W is equivariant with respect to diffeomorphisms, certainly. So you get a vector bundle over this space. And what can we do now? Never mind about the E business. You've got a point in here, is a point in the tangent bundle, and a bundle map from the tangent bundle to theta star of gamma D. And you can evaluate that function at that point. And you get a canonical bundle map, L, to the star of gamma D. I mean, you just got a function and a point element in the domain of the function. So this universal family has one more bit of structure, plus it has a theta structure on the relative tangent bundle. And then it's an exercise that I put on the exercise sheet, that this is a universal example of such a thing. I'm going to give this a name. Unit pi, comma, L universal is the universal such thing. I mean, any other example of such a fiber bundle with such structure is pulled back from some mapping to everything. Okay, that's a little exercise in what classifying space is classified, basically. Okay. Oh yeah. There's another description of this space, which is quite nice. And it's just interpreting what I've actually defined it to be. I'm going to be embeddings, of course, the structure is divided out by diff. So there's a set. What is that? There's a set that has the following description. You have a subset of minus infinity, 0, also infinity, which is a smooth manifold, and which is diffeomorphic to W, but not in a given way. Right? This is just the embedding of some random embedding of W into this space, but then you forget that it's an embedding, you just remember its image. Okay, so this is a smooth submanifold. Containing minus infinity 0 across E naught of the boundary of W. So it contains this column at least near 0.
Minus infinity?
Sorry?
Minus infinity or minus epsilon?
Okay, agreeing, let me say that, agreeing with this near 0.
Oh, okay.
Yeah. So it's that, such that, in that case, its boundary is exactly identified with the boundary of W, and the property it has is that relative to its boundary, there exists, but not in a given way, in order to W. Right? The image of an embedding has that property. Comma, the structure on X, which is itself a manifold. So this is some set, and it's projection, it's in bijection with this, and hence that gives us a topology as I said. And that's why I really want to think about these things. I don't want to think about embeddings, I just want to think about submanifolds which happen to be diffeomorphic to W, not in a given way. Good. Right, so that was another model for the same space, but it's actually, if you topologize it so those are the bijection, then of course it's homomorphic to it. And I want to give another model which is not homomorphic to it, but it's homomorphic equivalent. And now, again, I'll leave it as an exercise if you like to show that it is homomorphic equivalent. So for this, I now want to suppose that this map theta I start with is a fibration, which I can do just with replacing my fibration. And now if X is a point, a manifold of this type, so it's a manifold inside a half space, and let me suppose we're working in finite dimensions for now, and then I'll take the limit in a minute. So if X is a manifold like that, we get, in a canonical way, that a manifold inside the Euclidean space does have a canonical Gauss map. Canonical map from the manifold to the Grassmannian of D-planes in Rn that sends the point X on the manifold to the tangent space of the manifold at the point X. Pretty tautological. And by definition it classifies the tangent model. So guess a canonical.
N plus 1. N plus 1, yeah.
So get a canonical Gauss map. And now, for my BOD, BOD is just some homotopy theoretically defined thing. You get to choose what model you take, and I'm going to take the Grassmannian of D-planes in my infinity. Okay? So then I can just follow this, the inclusion of the Grassmannian of D-planes of Rn into the Grassmannian into R infinity, and now I can talk about lifts along this vibration. Because this map is now completely canonical, I don't have to worry about making choices. So let B, that's theta n, so Bn, so the Grassmannian of D-planes in Rn, we just call back So here's the second model I'd like to talk about. Tilde, you can remember the dimension, W or not. These things are the following flavour. So it's an X inside this space, just like before. It's an L, it's a lift along this vibration theta n of its now canonically defined Gauss map. Such that various things hold. One is that x equals minus 0, 0 equals E naught W 0 as usual. Another one is that this L tilde restricted to the boundary of x is equal to, I guess my boundary condition also ought to be of the lift type as opposed to the bundle map type, which is just equal to that. Also, that x runs to its boundary, there exists as if you walked into W runs to its boundary. So these are all basically similar, but there's one last thing that's a bit different, which is the following. Now I want to say, so the normal bundle of x has a canonical map into here. Right. So here I'm using the fact that everything inside in fact has a Riemannian metric coming from the standard metric on Rn. And I'm going to insist that when I restrict to the vectors of length at most 1, this is injective. Okay? So I want to think of these as being fat manifolds. So they all have a radius 1 tubular neighborhood. So the conditions of this is injective on the vectors. Most 1. Okay? These are fatly embedded manifolds. And now for any manifold, suppose we didn't have the boundary there at all. Okay? For any manifold, it has some injectivity radius on a normal bundle if it's compact. Suppose that's epsilon. Then if you scale it by 1 of epsilon, it now has injectivity radius 1. So in the case where there's no boundary, that I just proved that this model is almost equivalent to the old one. You can always suppose you have a big injectivity radius just by scaling the manifold. When you have boundaries, it's a bit more complicated, but not much more complicated.
You have to start with not too wiggly
On the
boundary
boundary,
variable
yeah.
to start with, otherwise it's empty.
Yes, yes. And then the fact that we can also relegate to the exercise session is that the modulus that to start with is almost equivalent to the limit of these as you let n go to infinity. Okay, so it's just a different model for the same space.
So what's the topology on
On this one, it's a bit annoying, right? Because we need X value and those value. Let's not worry about that. It's the obvious thing, right? I mean, what a continuous path is. Maybe the topology isn't obvious, but what its singular complex is, I claim is obvious. What a smooth path in this space should be, I claim is unambiguous. Okay? And then I claim that there is a topology on the space for which this continuous paths have smooth approximation, and the smooth paths are the ones that are obvious. That's actually proved in figure.
So for this statement that these are homotopy equivalent, it's really relevant that the map to BOD is an honest vibration.
Yes, exactly. Otherwise, I mean, there might just not exist any of these if you take the stupid. Like, suppose you want to do framings, right? So you take B to be a point mapping to BOD. Like, if its Gauss map happens to not hit that point, that doesn't mean it doesn't have a framing. Right, so it has to be a flavor.
I mean, you could rectify this by also requiring the diagram turning commutative to homotopy and fixing the homotopy.
But that's exactly the same as lifting up the vibration like this. Right, so this is just another model of a similar thing, but it's very good for Pontryagin Tom theory, this model. Because of this existence of a sort of canonical Tuber neighborhood that we know about. So what I want to say is, given x L tilde in this space, what can I do? Well, I can look at minus infinity 0 cos r n minus 1, and I can take the 1 point compactification of that. So, if you think about what that is, that's the same as minus infinity 0 smash n minus 1, where minus infinity is the base point of infinity. Okay? Now, 1 point compactification is contravariant, right? So I can collapse down the complement of this tubular neighborhood of length 1, and I get a canonical map to the Tom space of the bundle nu x. Right? Tom space is what? That's the unit disk bundle modulo the sphere bundle. And that's exactly what I'm dividing out by. Now, this L tilde business, L tilde is designed to pull back the d-dimensional bundle and get, you'll worry about this because I'm going to write equality between bundles and you might think I'm doing something silly, but I'm not. Tx. Okay? And this is equality, it's as subbundles of the trivial bundle over x. Everything in sight, the tangent, because everything's inside Rn, all these bundles are actually subbundles of the trivial Rn-dimensional bundle. And they're just equal subbundles. Okay? So, because they're equal, and I'm inducing the metric from Rn, if I pull back the orthogonal complement to that one, I get the orthogonal complement to that one, which is by definition the normal bundle x. Okay? And so there's a map induced by L tilde between Tom spaces. Okay? So this this gamma d perp, what does that mean? So on the Guasamanian of d planes in Rn, you have a d-dimensional bundle in a canonical way. You also have a canonical n minus d-dimensional bundle, namely all the vectors that are orthogonal to that. Okay, that's what I mean by perp. So this has dimension n minus d. Okay? Now I can adjoint over the sphere bit, and I get adjoint over the sphere bit, and I get a path minus infinity 0 to loops n minus 1 of this space here. Oh, sorry, that should be theta n, right? That's what I call it in the description. Okay? And this involved no choices. Because I built all the choices into this space, this tilde space, right? So you get a canonical map from this modular space to paths minus infinity, or maps like this, minus infinity 0 to loops n minus 1. Completely canonical way. And furthermore, what sort of maps do you get? Well, they're based at both ends. At the minus infinity end, it maps to the base point here. And at the 0 end, what does it map to? Well, it maps to the Pontryagin-Thom map to the boundary of W. Right? So you get it. So these are the paths from the empty manifold, as it were, or rather the Pontryagin-Thom map of the empty manifold, which is the base point over here, to the Pontryagin-Thom map of the boundary of W with its physical structure. Okay?
Maybe I'm slow, but I don't see why the Pontryagin-Thom construction is naturally appearing.
Sorry, say again?
I don't see why the Pontryagin-Thom construction is naturally appearing as the values of this map.
So, as the boundary, you mean?
Yeah.
So the picture is like this. We've fixed this embedding of the boundary, right? And we're looking at all things that fit in like that. And we're looking at all ones that are sufficiently thick. So they're normal bundle of radius 1 best. Okay? Right. And we draw that just on the boundary. Okay? Now we're doing the one-point compactification of the whole space, or the whole half space.
Oh, yeah.
Okay, yeah, we already.
Right? And in particular, that one-point compactifies the boundary. Right? And there you're just doing exactly the ordinary Pontryagin-Thom construction on the boundary.
Okay. Yeah.
Right. So now taking the limit as n goes to infinity and replacing this model by the other one, there's a map, or at least a homotopy class of map when we replace the model, between m theta w with this boundary condition to, let me write it this way, paths from the nth manifold to the boundary w on the space taking this and taking the limit as n goes to infinity. Okay? Now this is by definition the infinite loop space of a certain spectrum. Okay? This is, in fact, it's the -1 space, not the 0 space of the spectrum in the natural way, of mt theta. So this is defining a thing called mt theta. Mt theta is a spectrum which in degree n is this one space. So that's the spectrum in the sense of stable homotopy theory. If you're not familiar with that, maybe we should discuss these sort of things in the discussion session this afternoon. But by definition, what I've got is a map from this to paths on an infinite loop space, from the base point to another point. It's not the base point, but it's fixed. It's almost like the loop space again. In fact, if the boundary was empty, then it would be the loop space. Okay. Unfortunately, that was just part one. So now I want to fix the dimension to be even. So everything I've said so far is just analysis about manifolds, and there's no more theorems inside. So I want to tell you about a theorem. We fix the dimension to be even. Fix 2n-1 manifold with a P structure on it, so that's going to be my boundary. And the thing is, I want to look at all manifolds now that have that boundary. Not just fix a manifold and have its boundary and so on. I want to look at, I think of this as the modular space of null Bordisms of P. And this is defined to be the disjoint union of these things, where I take the disjoint union over manifolds W, such that two things hold. One is that the boundary of W is P, certainly. And secondly, that W is highly connected relative to its boundary. So this is n minus 1 connected. Okay, so I want to look at those null Bordisms of P that are highly connected and would have a theta structure. Okay? Now if
What's the equivalence relation on these W?
I take one in each diffeomorphism class of such things, let's say. There's no equivalence relation. Well, there is diffeomorphism, and I pick one representative for each class. So if I've got a Bordism between, oh, maybe I should have called that LP. It fits my later notation. So I've got a Bordism of theta manifolds between two P's, such that it's highly connected relative to both ends. Then gluing it onto a highly connected null Bordism gives a new highly connected null Bordism. And I get a map called sort of composition with K. And the null Bordisms of P to the null Bordisms of this. Right? And the picture is just that I've got another Bordism like that. Just glue on this K that way, and I get another Bordism of the other thing. And the theorem that I want to talk about tells you about the homology or cohomology of these spaces of null Bordisms, not as they are, but after you invert certain endomorphisms like this. So if you take P to be equal to P prime, you get an endomorphism of one space, and you can localize that in the homology. So it tells you about the limit of gluing on many, many Bordisms like this. That's the sort of theorem I'm going to talk about. So let me try to do that now. So much quicker, so much quicker.
You have to be very precise with all the coordinates and everything. Now in the gluing construction, you're a bit sloppy. We have to work out the
Bordism should be inside 0, 1 for some infinity. And you take union and then shift by one unit up. It's defined on the side.
But you knew that.
before I can say the theorem about the homology of these spaces, I need to give you some definitions so that you understand what the hypotheses of the theorem mean. One is that this tangential structure theta is called spherical if any theta structure on the lower hemisphere of a two-end sphere extends to the whole two-end sphere. Okay? So, examples, orientation, spin, things like that. Only interesting non-example really is framings. Another interesting one is almost complex structures, at least for n not 1 or 3. Okay?
Yes, another one is partial framings,
Right.
which is
Yes, like having a vector field. Right, so that's one definition. So this is just a hypothesis that nothing will be true without this, so I'll have that. More interesting one is called a sequence of composable theta cobordisms. So let me omit the theta structure. If a manifold now will have a theta structure implicit, and if the manifold is called M theta structure, we call it L sub M. Okay. So this notation is not a restriction of anything, but it's supposed to be a bit psychologically useful. So I have a sequence of composable cobordisms. It's called a universal theta end if the following properties hold. The first one is easy, which is that each of the cobordisms, I plus 1, is highly connected in this sense. It's n-1 connected relative to either end. So each one of these is n-1 connected, well, either end. So, but it's the second part that's much more interesting. The second part says the following. Let me just draw it as a picture first, and then I'll say something over there. Suppose I've got a Ki, and I've got some cobordism from that to something. The W, theta cobordism now, everything. And this is highly connected in the same sense. n-1 connected relative to both ends. I also have a cobordism from Ki, or longer, to K, I, comma, I plus K, sorry. This is the composition of K of these little ones. And the property 2 is that for any one of these, there's a K, it might be very big, so that that cobordism embeds into this cobordism relative to this end. Again, with theta structures and things. Okay, so it's called a universal theta end if it absorbs every highly connected cobordism in this way. So any W from Ki to something highly connected embeds into, and because this little K is not so important, you may as well sort of take the composition of all of these cobordisms and get a non-compact manifold. And say it embeds into K I infinity, which just means the obvious sort of infinite composition of these things. Well boundary and with theta structures. Okay? Now, it is not very obvious that universal theta ends exist. But it's true. In fact, they always exist. Given any K0, any K0 and any theta that's spherical, there's a sequence of cobordisms that have this graph. That's one of the technical things that we prove. I just want to give you some examples. Let's do BSO2 to BO2. then an example of a universal theta end in that case is a composition. All the cobordisms are the same, and they're all a torus with two boundary circles. Okay? Why is that a universal theta end? Well, it's similar, so we may as well take I be 0, right? You have some cobordism from a circle to something. It doesn't have to be a circle. And the property it has to have is this highly connectedness. So it has to be, in this case, 0 connected relative to this end. This end is a circle, so it has to be connected. So it's it can have many boundaries over here, and it can have homogeneous. And it has to have a theta structure. So it can't have a projective plane in it. It has to have an orientation. And we would have trouble embedding that in here. But it's just follows from the classification of surfaces that any such thing like that embeds into one of those. Right? When you do non-orientable surfaces, you can take a composition of many cylinder connects some RP2s, and any non-orientable surface embeds into that. Even an orientable one embeds into that, of course. You have to mix all of that. We have to go back an even number of these. So those are examples in dimension 2, and they're I think the ones to keep in mind for this this property.
But it does not rely, the general proof, on the classification.
No. Probably the general proof wouldn't work in dimension 2 because it's sort of by surgery.
Oh,
But,
okay.
yeah.
So where do you send it to open the boundary, just wherever you want? Or?
Yeah. It just has to embed. It doesn't have to line up with the slices. Okay. Yeah. I mean, if you glue on that, is it obvious that that embeds? Right. Yeah. If that embeds, then anything smaller does as well. Right? So there you go. Right. Okay. Now, I was going to say one thing, but I think I won't. So there's a homotopy theoretic characterization of this. There's a homotopy theoretic condition on theta that you can really check. It's about certain maps being injected and certain maps being surjective on homotopy groups that guarantees this being true. Maybe I'll say that next time if I have more time. So now I can say the main theorem. This is going to work with Sondalacious. So let 2n be at least 6, theta be spherical.
Excuse me, what was this statement? There is a criterion for theta to being spherical? Or
No, that's easy. I mean, that's just this. There's also a homotopy theoretic criterion if you want. There's a criterion for a theta, or for a collection of cobordisms to satisfy this property too. There's a homotopy theoretic criterion for that. Yeah.
Just for the existence of something?
Yeah. No. If you have a sequence, you can check whether it satisfies this property without messing around trying to embed manifolds into other manifolds. Just checking some things on homotopy. That's the theory. That's not obvious. Right, and this be a universal theta end, such that the first thing has a null bordism to the left. Otherwise, the space of null bordisms is going to be pretty dull. So this is not empty. Then the Contrarian Tom map that I discussed earlier now goes, you can take the limit, and it goes from the HOCO limb of these null bordisms of Ki, and I have all these stabilization maps between them, and I can take the HOCO limb as I goes to infinity by using these cobordisms. And it goes to the infinite loop space of MT theta prime, where theta prime is the following thing. So it's not the theta that you started with, it's a slightly modified one. The statement is then this Contrarian Tom map is a homology. It's a homology isomorphism where theta prime B prime to BO is a new tangential structure that's obtained in the following way. You have this K, and you have B, and K has a theta structure, so you have a map like this, LK, and you make the nth Moore-Postnikov factorization of that. So there's a universal, I mean, just by homotopy theory, there universally exists a factorization of this map, where this is n connected, and this is n co-connected. Let me write that out. So, and that determines this B prime up to unique, basically. So such that, if we look at homotopy groups, so pi ik, pi ib prime is isomorphism, it can be less than n, and epi can be n. And the other way around, pi I of b prime to pi I of b is isomorphism into b above n, and is mono into b n. So that's the Moore-Postnikov n stage. If you replace n here by k, it's the Moore-Postnikov k stage.
So who's K? I'm not confused.
Sorry?
What is K?
Ah, sorry, yeah, maybe I forgot to say that. K is just this non-compact manifold that you get by gluing together all these coordinates. Yeah. Okay.
So if you do the Moore-Postnikov stage of the manifold, say P, K restricted to 0, is this related? Is this the same?
That typically won't be the same. For example, I'd always say in the non-orientable surface case, P was a circle and the same P was a line. But there are different theta primes.
But sometimes...
Sometimes it'll be the same.
Yeah.
Again, there's an easy homotopy theoretic criterion if you want to check that. So, I just want to spend 5 minutes saying how you apply this theorem in an example. And this example will be relevant for the later positive scalar curvature lectures. So again, I take 2n and 6, so the theorem applies, and I take all of these cobordisms to be the same thing, namely a cylinder connects some Sn cross Sn. Okay? And I take theta. Theta n is the following. It's the map from the n connected cover of BO to n to itself, to BO to n, sorry. So this is the n connected cover. Okay? Now, some homotopy theoretic people might think I mean the n plus 1 connected cover, or n minus 1 connected cover by that. So my notation may not be your notation, but I mean n connected. Okay?
The talking group is K.
Sorry?
The nth group is K.
Yes, yeah, I've killed pi n, yeah, that's what I mean. I take theta to be that, and now, unfortunately, I've shot myself in the foot because I didn't give you this homotopy theoretic characterization of when something is a universal theta n. But I'll try to go through basically the proof of that in this case. Okay? So I suppose I have, let me try to do that here. Suppose I have some cobordism from a sphere to something, which is n connected relative to both ends, and which has one of these structures on it. Okay? So by standard handle body theory, I can very nearly make it only have handles of index n relative to that end. I can make it have handles of index n and n plus 1 just by handle trading. And then there's a small obstruction to getting rid of the last one. But you can always kill that by gluing on one of these things to connect some SA plus SA. And as usual, if I can embed a bigger thing in the thing, then I can embed a smaller. Okay? So I can make my problem a little, in principle, harder, so that it only has handles of index n relative to that. So if I want to embed an arbitrary cobordism that only had handles of index n, I may as well suppose it only had one handle of index n. I'll embed them one by one. Okay? So I've reduced to the case where you have a single n handle relative to that end, and the manifold has a theta. Okay? Now, because this is n connected, you can't have any funny business going on with the normal bundle of this n handle. That's exactly how you use this. Okay? So basically, it's just how to calculate that. And what is the thing in that case? Well, it doesn't quite have to be a connect on SN plus SN, but it has to be a summand of a yeah, maybe I can't quite say that in full detail now. But you see, these sort of criteria reduce it to doing something with a single handle. You can use, for example, immersion theory to immerse that handle. Then you can use this Whitney trick, or you can try to do a Whitney trick where you use all these extra SN plus SNs to undo intersection points, for people who know that technique. And that embeds this handle into the infinite composition of these. And that's basically a scaled down version of the general homotopy theoretic proof. Is what these things equals. So this sequence is a universal theta end in this example. And what you get out of this is, there's one more point, which is that if W is n-1 connected well boundary, then the space of theta structures of this form on W boundary is either empty or contractible. So that's a little obstruction theory proof using the fact that W is supposed to be n-1 connected relative to its boundary, and that this map is n co-connected. And then it's a little obstruction theory proof that the space of Lifts is either empty or it's contractible. And this manifold, so clearly this manifold is not empty, so it's compatible. And that means that my theta moduli spaces, the bundle data plays no role. It's just a model for the classifying space of the diffeomorphism of the manifold. So the end result is that the classifying spaces of a connect sum of G copies of Sn cross Sn minus a disk, but we take diffeomorphisms well boundary. That's what you get by taking a finite composition of these and gluing in one disk, I think. Has a map Luke's infinity MC theta n. You can check in this case that theta prime equals theta. Again, that's you just do a little calculation with the Will-Poisson property. Is a homologous force. So that's how you apply it in one example. I'm afraid I couldn't do this properly because I didn't do this and I time to do the homotopy characterization. But if anybody wants to know that, I'm happy to answer questions about it. So in the scalar curvature part of the lectures, in the last two lectures, we're going to apply this just when n is 3, in fact. So connect sum of S3 equals S3s. In that case, the 3 connected cover of BO is the spin. But in that case, this is something about spin cobordism. And that's what's going to show up there. Okay? So it's only this example we're actually going to use. Next lecture, I want to spend some time explaining some of the techniques that are involved in proving this sort of theorem. Unfortunately, the proof is very long, and I won't be able to tell you everything about it, but I want to give you some of the main geometric ideas. Thank you. Question?
When you write homology isomorphism, is that with any coefficients or rational?
Integrally.
Integrally.
Yeah. And therefore, we send it with any untwisted curve.
And you.
Yeah.
Maybe I missed it, but what were the cases where you can guarantee the existence of those universal feature ends?
Basically,
I think you said it orally, but I missed it.
always. So the statement is so not only let me tell you about that. If you fix this manifold, then there exists a sequence of these that's universal theta end.
And it hasn't to be spherical.
No, it does. Yeah, it does actually. So sorry. Yes, that's the condition.
Okay.
Yes. And furthermore, given any two universal theta ends, the non-compact manifolds you get by gluing them together are diffeomorphic relative to this end. So not only do they exist, but it's basically unique. The way you cut it up into individual cobordisms isn't unique, but the non-compact manifold you get is basically unique.
How far does the the limits depend on how you cut that? You know,
It's not at all. It only depends on the non-compact manifold. Another way of writing this here.
so the status is too long, isn't it? I mean, couldn't you then just, I mean, to get the map properly, you have to cut it up all the way?
Yeah, the map depends on how you cut it up.
Okay.
But this limit doesn't, because of some cofinality. Another way of phrasing this on the B-diff level is there's a non-compact manifold given by gluing together countably many of these and then gluing in a disk at one end. And it's something about the compactly supported diffeomorphisms of that one manifold. Not exactly the same.
So you said that the map itself technically depends on how you cut it up, but you get homotopic things.
So there's actually a map, I lied a bit here because if you remember the map I actually defined landed in a path space. And I've secretly been choosing paths from wherever they end back to the base point.
Okay.
And all that sort of stuff depends on how you cut things up. But probably any two maps differ via automorphism of the right-hand side. It doesn't depend very significantly, but on the point set level it depends.
I think myself. Do you, I mean, I've only ever seen you talk about this sort of case. Yeah, no, choosing these connective colours like the structure, the status structure. But do the others appear? I mean, also the examples you gave of spherical thetas are of this form. Are there other interesting ones? And what do you get from those?
So the way, there are lots of interesting ones obtained in the following way. If you've got some manifold you want to study, in principle it has no structure at all, maybe it's orbited or something. It has much B02N. And you can take the Moore-Postnikov stage of that. That's some structure that W has a given one of.
Okay, and then you compute the diffeomorphism group with the stabilization of W.
Unfortunately, the fit is not much of an algorithm, you see. You need to be able to find these two pieces of data simultaneously. Yeah, I mean, finding the theta and finding the universal end, you can play them off against each other. You can find them simultaneously satisfying the property. And sometimes, if you've got the universal, I mean, what's implicit over here with this theta prime business is that the universal theta end is also a universal theta prime end. That follows by this homotopic characterization I was saying there. So really, you could just say, suppose this map is n-connected, and then you don't have to do the replacement. And the things that are universal ends is the same class of sequences. There's various things you can play off against each other.